Hello, my name is Shahriari, and this is a lecture in a series of lectures on general topics in undergraduate mathematics. The topic of this lecture is posets. Some version of this topic appears in my An Invitation to Combinatorics. Another version appears in my abstract algebra book, Algebra in Action, a course in groups, rings, and fields. The ordinary integers are an example of a totally ordered set. The way we usually think of them is sitting on a number line. I've put them vertically so that we know that some numbers are bigger than the other ones. The bigger ones are higher up. The reason I call both the integers and the real numbers totally ordered is because they have the following properties. If you take two integers or two real numbers, either one of them is less than or equal to the other, or the other one is less than or equal to the first one. Every number is less than or equal to itself. If x is less than or equal to y and y is less than or equal to z, then x is less than or equal to z. And finally, if you have x less than or equal to y and y less than or equal to x, then x and y are equal. The subsets of 1, 2, 3 ordered by inclusion are not totally ordered. They're an example of something we call partially ordered. Here are all the subsets of 1, 2, 3, and I've put a line if some subset is contained in another one and their sizes differ by 1. And the properties that they have is the following. Any subset is a subset of itself. If A is a subset of B and B is a subset of C, then A is a subset of C. And if A is a subset of B and B is a subset of A, then A equals B. The thing that they're missing to be a total order is that some of the sets are not comparable. For the integers, if you pick two integers, you could always say that one is less than or equal to the other. But for subsets, that's not true. If you take the subset 1, 2 and the subset 2, 3, those are incomparable. Neither one is a subset of the other. There are many examples of partially ordered sets. For example, if you take divisors of 24 and think of the order as divisibility, here I have all the divisors of 24, 8, 12, 4, 6, 2, 3, and 1. If you see an edge, it's because the higher number is divisible by the lower number, and there's no other divisors between them. These have the same properties as subsets. Any number divides itself. If A divides B and B divides C, then A divides C. And if A divides B and B divides A equals B. Now, inside a partially ordered set, you could have a totally ordered subset, and usually we call that a chain. For example, here, 1, 2, 6, 12, and 24 form a chain. They are totally ordered because between any two of them, one of them is divisible by the other. Informally, a partially ordered set or poset consists of a set. It could be numbers, it could be subsets, it could be divisors of an integer, it could be other things, and a relation. That relation could be less than or equal to, it could be inclusion, it could be divisibility. So some elements are related to some of the others. And the relations on the set is reflexive. Everything is related to itself. It's transitive. If A is related to B and B is related to C, then A is related to C. And anti-symmetric. If A is related to B and B is related to A, then A equals B. So what is a relation? If you have a set, a relation on P is just a subset of P cross P. What is P cross P? P cross P is the set of ordered pairs of elements of P. So elements of the form parentheses X, Y, where X and Y are in elements of P. So if you have a set P, to make P cross P, you make these pairs where both entries are coming from P. And when you say you have a relation, you mean that some of the X's are related to some of the Y's. As soon as you say that Fred is related to Jerry, then Fred comma Jerry, that's one element of your subset. When you give me a relation, you're really giving me a subset of P cross P. If the pair XY is in the subset, then we say that X is related to Y, and usually we have a symbol such as squiggle, R for relation, or less than or equal to, that we use for that relation. Now, if squiggle is the relation and X is related to Y, then we just don't keep saying X is related to Y, we write X squiggle Y. Now, what's a partially ordered set? If P is a set and you have a relation on elements of P, so all that means is that if you give me two elements, you can tell me if this guy is related to that, or that's related to this, or maybe neither, or both. Then this guy is a partial order on P if for all elements of P we have the following properties. We have reflexivity, X is related to X. If X is related to Y and Y is related to Z, then X is related to Z, transitivity, and anti-symmetric property. If X is related to Y and Y is related back to X, then X and Y must be the same. If you have a partial order, then we usually use less than or equal to instead of squiggle. Now, some partial orders come with their own symbol, and we continue to use those. But if you have a generic partial order, we usually use less than or equal to, it doesn't mean we're talking about numbers. It means that we're talking about elements of a partial order, and the less than or equal to is that relation. A set with a partial order is called a partially ordered set, or a poset for short. If every pair of elements are comparable, meaning that either one is related to the other or the other is related to this, then we have what's called a total order. If you have a totally ordered subset of a poset, we call that a chain. So here's an example of a poset. The set P is the students in a combo class, combinatorics class, on April 14, 2025. If you pick X and Y and P, I'm going to define for you the relations. I'm going to tell you when X is less than or equal to Y. These are not numbers, these are students, and I'm going to tell you when X is less than or equal to Y. And I will have two criteria for X being less than or equal to Y. If X and Y are the same, then I'll say X is less than or equal to Y. Otherwise, I will say that X is less than or equal to Y if, compared to Y, X has eaten fewer gummy bears that day. Fewer, not fewer or equal to, but fewer gummy bears that day. So let's see if this is a partially ordered set. First of all, by definition, everybody is less than or equal to itself. And if X is less than or equal to Y and Y is less than or equal to Z, then X is less than or equal to Z. Because in either one of those cases, either the two are actually equal, or one has eaten fewer gummy bears than the other. If X has eaten fewer gummy bears than Y and Y has eaten fewer gummy bears than Z, then X has eaten fewer gummy bears than Z. And if X is less than or equal to Y and Y is less than or equal to X, what does that mean? If X is less than or equal to Y, there's two options. It could be X equals Y, that's what I want. But if it's not, then that would mean that X ate fewer gummy bears than Y. And Y less than or equal to X, again, could mean that Y equals X. But if it doesn't, then it means that Y ate fewer gummy bears than X. And X can't have eaten fewer gummy bears than Y, and Y have eaten fewer gummy bears than X. So the only way for both X less than or equal to Y and Y less than or equal to X to be true is if X actually equals Y. So this less than or equal that I defined is a partial order on this set, and P with that relation is a poset. Usually when we have a relation, we write the set, comma, and then the name of the relation, put it in parentheses, and we say that's a poset. So we are telling you what the set is and what the relation is. A prototypical example of a poset is the Boolean lattices. Bracket n stands for a set with n elements, 1 through n. The set of subsets of n, we denote that by boldface 2 to bracket n, is the set of subsets, and inclusion is a relation. When is something related to something? If the first thing is a subset of the second. This guy is a poset, and it's called the Boolean lattice of order n. And it's a poset because every set is a subset of itself. If A is a subset of B and B is a subset of C, then A is a subset of C. And if A is a subset of B and B is a subset of A, then A equals B. A little bit more vocabulary about posets. If you have a poset and two elements, then it's possible that X is less than or equal to Y, or Y is less than or equal to X, or neither. If it was a total order, then one of those two things would be necessarily true. But for a poset, it doesn't have to be either one of them is true. If it's a fact that X is less than or equal to Y, or Y is less than or equal to X, then we say that X and Y are comparable. Otherwise, we say they're incomparable. For example, in the Boolean lattice of order 4, that's the subsets of a set with 4 elements ordered by inclusion. The subset 1, 2, that's a subset of 1 through 4, and 1, 3 is also a subset. They're incomparable because neither one of them is a subset of the other. On the other hand, 2 and 1, 2, 4 are comparable because 2 is a subset of 1 through 4. Now, if X is less than or equal to Y, but they're not equal, then we write it as X less than Y. And if X is less than Y, and there's no Z between those, so there's no Z that's bigger than X and less than Y, then we say that Y covers X. Y is immediately above X. Y covers X, or X is covered by Y. For example, in the Boolean lattice of order 5, 1, 3, 5 covers 1, 5. That's because 1, 5 is less than 1, 3, 5, and there's no subset between them. There's no subset that contains 1, 5 and is contained in 1, 3, 5 and is neither one of those. On the other hand, 1, 3, 5 does not cover 3, even though 3 is a subset of 1, 3, 5. 1, 3, 5 doesn't cover it because 1, 3, for example, is a subset that lies between the two. Now, given a finite poset, we have a visual way of thinking about it. We can draw something called its Hasse diagram. First, let me give you an example, then I'll give you the definition. So Hasse diagram of the Boolean lattice is what I'd shown you before. And if you forget the labels, it's a cube. Let me define it formally. If you have a poset, the Hasse diagram is a graph The vertices of this graph are elements of the posets, and if x and y and p, you put an edge between x and y if and only if y covers x. So you don't put an edge whenever there's a relation, only when there is a cover relation. And that way the graph is less cluttered, but it has all the information. And also if x is less than y, then we draw x lower than y. For example, this could be the Hasse diagram of a poset. Now again, in a poset, one of the relations is reflexivity. Everything is less than or equal to itself. That's not explicitly mentioned in the Hasse diagram, like we don't have loops, but that's assumed. Also, another relation is transitivity. If x is less than or equal to y and y is less than or equal to z, x is less than or equal to z. We haven't drawn those. That would have cluttered the picture too much, but that's assumed because what we have drawn are the cover relations. We know that x is less than or equal to y and there's nothing between them, and y is less than or equal to z, nothing between them, but we know from transitivity that x is also less than or equal to z. Hasse diagrams are named after the German mathematician Hasse. Hasse was a very prominent mathematician with extraordinary accomplishments in number theory, but his past was controversial because he lived during World War II in Germany, and in fact, he applied to be a member of the Nazi Party, although his application was denied because in his ancestry, they decided there was some Jewish blood. He was a prominent mathematician and made contributions in many fields, but his legacy is somewhat tainted. This is the Boolean lattice of order 6, all the subsets of 1 through 6 ordered by inclusion. Here, I've not put the curly brackets and the commas because I would not be able to draw it on one page. Here's the Hasse diagram of the integers. We have seen this before, ordered by less than or equal to. And this is divisors of 24, as we have seen before, ordered by divisibility. I have a whole other video for posets that come up in combinatorics. Lots of things that we count. You can think of the things we count as a part of a poset, and we have a whole video just on those. What posets do for you is that they allow you to put a structure on the elements of a set that you're investigating, and that structure might be helpful. I'm going to give you some examples from linear algebra and algebra. If you're just interested in combinatorics, you can ignore the next few slides. If V is a vector space and we look at all the subspaces of V, then ordered by inclusion, that gives us a poset. For example, here's the Hasse diagram of the subspaces of R3 ordered by inclusion. R3 has infinite number of subspaces. There is the 0 subspace at the bottom, the one that just has the vector 0 in it. And this first level, they're all the one-dimensional subspaces, which are the span of one thing, like 1, 0, 0. The subspace generated by that. That includes elements like 1, 0, 0, 2, 0, 0, 5, 0, 0, minus 3, 0, 0, pi 0, 0, and so forth. Then the span of 0, 1, 0, for example, so on and so forth. There's an infinite number of these subspaces of dimension 1. Then we also have subspaces of dimension 2, and we have one subspace of dimension 3, which is all of R3 itself. For example, if I look at the span of 1, 0, 0, and 0, 0, 1, among the ones that I've listed here, it only includes the span of 1, 0, 0. Of course, it has a lot of other subspaces that are at this level, but I just haven't mentioned them. 1, 0, 0, and 0, 1, 0, the two of them span. They include 1, 0, 0. They also include 0, 1, 0, and they include 1, 1, 0. So these guys are subspaces of those and so forth. So you can think of subspaces of R3 in this way. If the field of scalars was not the real numbers, but was a finite field, then you would get a finite poset. In group theory, posets come up also. If you look at the subgroups of a group, for example, then LG, ordered by inclusion, is also a poset. For example, if you look at our favorite group, the dihedral group of order 8, I have a whole video just on the dihedral group of order 8. If you don't know what I'm talking about and you want to know, just go watch that video. That's a group generated by two elements, one of order 4, one of order 2, and then BA is not AB, but it's a cube B. D8 is symmetries of a square. A is the 90-degree rotation counterclockwise, and B is a reflection. Here's the Hasse diagram of it. So these are all the subgroups of D8 ordered by inclusion. And in group theory, we can get very far if we know this poset. Watch my videos on the lattice of subgroups of groups in my algebra collection. Also in ring theory, the set of ideals in a ring ordered by inclusion also form a poset. Now, there's certain kinds of posets that have their own name because they're special. So if P is a poset, P is called a lattice if every pair of elements has a least upper bound and a greatest lower bound. So what's the least upper bound? If you have a pair of elements, the least upper bound is an upper bound for both of them. That means that it's greater or equal to both of them. But also it's the smallest such, and it's the least. So that means that it's smaller than any other upper bound. And the same thing with greatest lower bound. So it's something that's less than or equal to both elements, but it's greater or equal to any other lower bound. So by definition, a least upper bound, if it exists, then it's unique. And the same with the greatest lower bound. If you have that, then you have a lattice. Now, the Boolean lattice is a lattice. That's why it's called a lattice. And if you have two subsets of a set with n elements, then their intersection is their greatest lower bound. If A and B are subsets, then A intersection B is their greatest lower bound, and their union is the least upper bound. If you look at poset of subspaces, that's also a lattice. If you have two subspaces of a vector space V, then their intersection and their sum is their greatest lower bound and least upper bound, respectively. If you don't know what the sum of two subspaces is, watch my video in the linear algebra section that talks about that. Poset of subgroups is a lattice. If you have two subgroups, then again, their intersection is their greatest lower bound. The least upper bound is the subgroup generated by H and K. If you are in a abelian group, that would be HK. But in general, that might not be. In fact, it will be HK if HK equals KH. There's a whole set of videos on those. Now, one last thing that I want to talk about is poset isomorphisms. When are two posets the same? Of course, two posets are actually the same if they have the same elements and the same relations. But often there are posets that maybe don't look the same, but really as far as being a poset are concerned, they are identical. They don't have any poset properties that are different from each other. And just like in other areas of mathematics, we call such posets isomorphic to each other. So if you have two posets, and if you have a map, a way of translating from P to Q, that's called a poset isomorphism. If it's one-to-one or onto, it means that you're pairing elements of P and Q. You're saying this element pairs with this one, translated to that one, and so forth. For every element in P, you've identified a unique element in Q, and vice versa, that they correspond to each other. But more than that, X is less than or equal to Y in P, if and only if their images, phi of X, is less than or equal to phi of Y in Q. So what that means is that you can relabel the elements of P and you will get the poset Q. If there is a poset isomorphism from P to Q, then the two posets are called isomorphic. So for example, as an example, the poset of divisors of 36 and the poset of divisors of 100, both ordered by divisibility, are isomorphic. And the easiest way to see that is to look at their Hasse diagram. If you look at their Hasse diagram, the map is clear. 1 goes to 1, 2 goes to 2, 3 goes to 5, 4 goes to 4, 6 goes to 10, 9 goes to 25, 12 goes to 20, 18 goes to 50, and 36 goes to 100. And the relations are identical, as we see from the Hasse diagram. There are 16 posets of size 4, for example, and here the Hasse diagram of all of them. And you could go through and try to decide which one of these are lattices, for example. If you look at the top right one, this is not a lattice. Why? Because if you take these two bottom points, what's their least upper bound? Is it this guy or that guy? There are two options, and that can't be a least upper bound because neither one of them is less than or equal to the other. So it doesn't pass the test of being a least upper bound. It's a lesser upper bound, but it's not a least upper bound. It's not smaller than every other upper bound. And this one is also not a lattice because these two guys, what's their least upper bound? They're actually nothing above them. In studying posets, there's two general attitudes or ways of going about it. It might be that you want to start with small posets, like these posets of size 4, and try to see whatever statement you're making, does it make sense for these? Start from simple, easy posets and make your way up. The other attitude, the one that I take, is that you start with posets that have a lot of structure. So you start with the Boolean lattice and take that as your prototypical example, the subsets of a finite set ordered by inclusion. Then you try to look at posets that behave like it. You try to say that, okay, I know a lot about sets. What about them also manifests itself in other posets? This is the end of this lecture. Keep hydrated at all times. Like my videos if you like them. And if you want to be subjected to more videos like this, then subscribe to my channel. See you at the next lecture.